Space has always been the ultimate frontier of the unknown, a vast, silent expanse where the rules of our world seem to bend and twist into something stranger than fiction. And when it comes to asteroids, those ancient, wandering rocks drifting through the cosmos, they hold secrets that defy even our wildest imaginations. Picture this: chunks of rock, some as small as a car, others as massive as mountains, carrying clues to the origins of our solar system and occasionally something far more unexpected. Scientists have spent decades studying these celestial nomads, and what they've found will make you question everything you thought you knew about the universe. From metallic anomalies that shouldn't exist to traces of materials that hint at cosmic mysteries we can't yet explain, asteroids are more than just space debris. They're time capsules hiding stories billions of years in the making. But here's where it gets really strange. Some of these discoveries are so bizarre, so utterly out of place, that they've left researchers scratching their heads. Imagine a hunk of rock hurtling through the void, only to reveal traces of organic compounds, ingredients for life, just floating out there in the darkness. Or consider the asteroid that seemed to be covered in a substance eerily similar to rust, except there's no liquid water in space to create it. How? Why? These aren't just curiosities, they're cosmic puzzles that could rewrite the textbooks. And today, we're diving deep into 25 of the most mind-bending, spine-tingling finds ever made on these wandering space rocks. This isn't just a list, it's a journey into the unexplained. Each of these discoveries peels back another layer of the universe's strangeness, revealing a side of space that feels more like science fiction than reality. Some will make you wonder if we're truly alone out there. Others might leave you staring at the night sky, questioning what else is lurking in the shadows of our solar system. So buckle up. By the time we're done, you'll never look at asteroids the same way again. The cosmos is far weirder than we've been taught, and the truth is waiting just beyond the next orbit. The first jaw-dropping discovery on our list might just rewrite the story of life itself: organic molecules found on asteroids. We're not talking about simple space dust here, but complex carbon-based compounds, the very ingredients that make up life as we know it. This isn't some fringe theory. Missions like Japan's Hayabusa 2 and NASA's OSIRIS-REx have brought back samples from asteroids Ryugu and Bennu, and what they found has sent shockwaves through the scientific community. These tiny grains of rock contained amino acids, the molecular building blocks of proteins, just floating out there in the void. Now, here's why this is mind-blowing. For decades, we assumed life's chemical precursors could only form in the presence of liquid water or under Earth-like conditions. But these asteroids, barren, airless, and exposed to the harsh radiation of space, somehow cooked up these crucial ingredients anyway. It's like finding a fully set dinner table in the middle of a desert where no one's ever lived. Take Ryugu, for example. This diamond-shaped space rock, barely half a mile wide, turned out to be packed with organic material, including uracil, a key component of RNA. That's right, one of the molecules essential for genetic coding was just sitting on a random asteroid, waiting to be discovered. And Bennu, its samples contained even more surprises. Scientists identified glycine, the simplest amino acid, alongside other carbon-rich compounds that hint at a cosmic chemistry lab far more sophisticated than we imagined. These findings suggest that the raw materials for life might be scattered across the solar system, hitching rides on asteroids since the dawn of time. Suddenly, the idea that life on Earth was kickstarted by materials delivered from space doesn't sound so far-fetched. But here's the twist: some of these molecules shouldn't exist where they were found. Space is a punishing environment with extreme temperatures, ultraviolet radiation, and no protection from cosmic rays. Yet somehow, these delicate organic compounds survived, almost as if nature found a way to preserve them like cosmic time capsules. That raises a tantalizing question. If asteroids carried these building blocks to Earth, could they have done the same for other worlds? The implications are staggering. Life might not be a rare accident confined to our planet, but something the universe has been quietly assembling everywhere, one asteroid at a time. What's even more fascinating is how these discoveries challenge the timeline of life's origins. If complex organics were already forming in the early solar system, then the process could have started billions of years earlier than we thought, maybe even before Earth was fully formed. It's like uncovering a hidden chapter in the story of existence, one where asteroids weren't just silent rocks but active players in seeding the cosmos with life's potential. And with every new sample, every new discovery, we're getting closer to understanding just how ordinary or extraordinary our own origins might be. If organic molecules weren't shocking enough, how about this asteroids carrying vast reserves of water ice just floating in the vacuum of space? It sounds impossible, right? Water needs certain conditions to exist, and the freezing, airless void between planets shouldn't be one of them. Yet, missions like Dawn to Ceres and observations of asteroids like 24 Themis have proven otherwise. These cosmic wanderers aren't just dry, dusty rocks, they're hiding frozen water, sometimes in staggering amounts. Take Ceres, the largest object in the asteroid belt. When NASA's Dawn spacecraft arrived in 2015, it spotted something extraordinary: bright, reflective patches scattered across the dwarf planet's surface. These turned out to be deposits of water ice, some hidden in permanently shadowed craters where sunlight never reaches. But here's what's even wilder: Ceres isn't alone. Asteroid 24 Themis, a much smaller body, was found to have water ice coating its surface, exposed to the harshness of space. So how does water ice survive on these barren rocks? The answer lies in the delicate balance of temperature and protection. In the darkest, coldest pockets of an asteroid, like the bottoms of deep craters, temperatures can plunge so low that water molecules stay frozen for billions of years. Some asteroids might even have subsurface layers shielded by loose dirt or rock, acting like a cosmic freezer. And then there's the possibility of water being chemically bound in minerals, locked away until conditions change. But why does this matter? Because water isn't just for drinking. It's the key to humanity's future in space. Break it down, and you get oxygen for breathing and hydrogen for rocket fuel. Suddenly, asteroids aren't just scientific curiosities, they're potential cosmic gas stations, fueling missions deeper into the cosmos. Imagine a future where astronauts mine water from asteroids instead of hauling it from Earth, slashing the cost and risk of long-distance space travel. Companies like Planetary Resources have already floated this idea, eyeing near-Earth asteroids as stepping stones for exploration. There's an even bigger implication here. If water ice is common on asteroids, then similar deposits could exist on the Moon, Mars, or even the moons of Jupiter and Saturn. It suggests that the solar system might be far wetter than we ever imagined, with frozen reservoirs scattered everywhere. And where there's water, there's potential for life, or at least the conditions to support it. The discovery of water ice also throws a wrench into our understanding of how Earth got its oceans. One prevailing theory suggests that comets delivered water to our young planet, but asteroids could have played a major role too. Unlike comets, which are mostly ice, asteroids are packed with minerals, meaning they could have brought both water and the building blocks of life in one package. But the real mystery is how this water ice stays stable. Space isn't kind to exposed ice. Solar radiation should break it apart over time. Yet on asteroids like Themis, it's still there. Some scientists think a thin layer of dust might act like sunscreen, protecting the ice underneath. Others speculate that these asteroids are constantly replenishing their ice through some hidden process we don't yet understand. One thing's for sure, every new discovery about water in space forces us to rethink what's possible. If asteroids can hold onto water ice for eons, what else might they be hiding? And if we can tap into these cosmic reservoirs, the entire solar system suddenly becomes a little more within reach. Now let's shift our gaze to an asteroid so strange it feels ripped straight from a sci-fi novel, Psyche, a world not of rock but of metal. This isn't just an asteroid with traces of iron. It's a colossal, misshapen chunk of nickel and iron, roughly the size of Massachusetts, drifting between Mars and Jupiter. But what truly sets Psyche apart isn't just its composition. It's the mind-bending possibility that this metallic giant might once have had volcanoes. Not the fiery, lava-spewing kind we know on Earth, but something far more alien, metallic volcanoes. Imagine a volcano, but instead of molten rock, it erupts with liquid metal, rivers of iron and nickel bubbling up from deep within the asteroid's core, oozing across its surface before cooling into twisted, otherworldly landscapes. This isn't wild speculation. It's a serious theory backed by scientists studying Psyche ahead of NASA's upcoming mission. The clues lie in Psyche's bizarre surface features, scarred by what appear to be ancient channels and ridges that look eerily similar to lava flows, except they're made of metal. Here's why this rewrites the rules of planetary science. Volcanic activity, as we've always understood it, requires heat, pressure, and molten material. On Earth, that material is rock, but Psyche challenges that assumption by suggesting that metals, under the right conditions, can behave like geology's version of a liquid. If true, it means the early solar system wasn't just a place of molten rock and gas. It might have been a realm where metal worlds churned and erupted in ways we've never witnessed. The implications are staggering. Psyche isn't just a fossil from the dawn of the solar system. It could be a snapshot of a planet's core frozen in time. Most rocky planets, including Earth, hide their metallic cores deep beneath miles of rock, utterly inaccessible. But Psyche seems to be the exposed heart of what might have once been a much larger body, a protoplanet torn apart by violent collisions billions of years ago. Studying it could give us an unprecedented look at the building blocks of planets, revealing secrets about how Earth's own core formed. And then there's the bigger question: how does a metal volcano even work? On Earth, volcanoes erupt because of heat from radioactive decay and the planet's internal pressure. But Psyche's metallic eruptions would have required a different recipe, perhaps residual heat from its violent formation, or even collisions that liquefied its surface. Some scientists speculate that sulfur or other elements mixed with the metal could have lowered its melting point, allowing it to flow like lava despite the cold vacuum of space. The mysteries don't stop there. If Psyche had active metal volcanoes, did they spew jets of liquid iron into space? Could they have created bizarre metallic clouds or even rain? These aren't just poetic musings, they're real possibilities that could reshape how we think about geology on other worlds. Jupiter's moon Io, with its sulfur volcanoes, already showed us that alien geology exists. Psyche might take that a step further, proving that the universe has a far richer, weirder vocabulary of planetary processes than we ever imagined. NASA's Psyche mission, launching soon, aims to answer these very questions. The spacecraft will map the asteroid's surface, analyze its composition, and search for definitive signs of those theoretical metallic eruptions. If confirmed, the discovery wouldn't just be a footnote in astronomy, it'd be a revelation, forcing us to rethink the very definition of a volcano and expanding the list of ways planets can evolve. Until then, Psyche remains one of space's most tantalizing riddles. A metal world with the potential to rewrite textbooks. It's a reminder that the universe doesn't just defy our expectations, it obliterates them. And as we inch closer to uncovering its secrets, one thing's certain: the deeper we look into the cosmos, the more it feels like we're reading a story written in a language we're only just beginning to understand. Asteroids aren't just cosmic rubble. Some of them are hiding treasures that would make even the most extravagant jewelers gasp. Scientists have found certain space rocks sprinkled with something utterly unexpected, diamond-like carbon structures. These aren't the glittering gems you'd find in a ring, but microscopic crystals forged under conditions so extreme, they defy earthly logic. Imagine the force of two asteroids colliding at speeds faster than a bullet, generating pressures millions of times greater than our atmosphere. In that split-second chaos, carbon atoms get squeezed and rearranged into structures eerily similar to diamonds, locked inside the rock like tiny, indestructible time capsules. What makes these discoveries so baffling isn't just their existence, it's what they reveal about the violence of the early solar system. Take the asteroid 208 catastrophe, for example. When researchers analyzed fragments that landed on Earth, they found lonstellate, a rare form of diamond even harder than the conventional kind. This stuff doesn't form under normal planetary conditions. It requires a shockwave of unimaginable force, the kind you'd only get from a collision so brutal it could shatter worlds. And yet there it was, tucked inside an asteroid like a cosmic secret. But here's where it gets even stranger. These diamond-like structures aren't just random accidents. They're clues pointing to a time when the inner solar system was a demolition derby of protoplanets smashing together, breaking apart, and reforming in a chaotic dance. Every lonstellate crystal is like a fingerprint from one of these apocalyptic crashes, preserved for billions of years. Some scientists believe these minerals could only form inside the cores of ancient, Mars-sized bodies that no longer exist, planetary ghosts whose remains now drift as asteroids. The implications stretch beyond mere curiosity. If asteroids carried diamonds forged in collisions, they might also hold answers about how Earth itself avoided annihilation. Our planet's survival depended on a delicate balance of impacts, enough to deliver water and organic materials, but not so many that they sterilized the surface. By studying these diamond-bearing asteroids, we're essentially reading the solar system's violent autobiography, written in atomic structures no earthly process can replicate. And then there's the practical side. Materials like lonstellate aren't just scientific novelties, they're potential game changers for technology. On Earth, we've struggled to synthesize this ultra-hard diamond variant in labs. But out in space, nature's been manufacturing it for eons, no factories required. The idea of mining asteroids for supermaterials sounds like sci-fi, but with discoveries like these, it's inching toward reality. Imagine drills coated in asteroid diamonds that never wear out, or unscratchable spacecraft hulls built from cosmic collision remnants. Yet the biggest mystery remains: how widespread are these diamond factories? Recent studies suggest they might be more common than we thought, hiding in plain sight among near-Earth asteroids. Some researchers even speculate that certain meteorites, once dismissed as ordinary space rocks, could be littered with microscopic diamonds we've overlooked. Every new sample we examine seems to rewrite the rules, proving that the universe has a flair for turning destruction into something dazzling. So the next time you gaze up at the night sky, remember, those unassuming specks of light might just be cosmic treasure chests carrying the shattered remains of lost worlds and the diamonds they left behind. It's a reminder that even in the void where chaos reigns, there's beauty forged in the fires of catastrophe. And who knows, the next glittering surprise might already be tumbling toward us, hidden in the belly of some wandering space rock. Magnetic fields shouldn't exist around asteroids, at least. That's what scientists thought until they stumbled upon one of space's quietest contradictions. These barren, lifeless rocks, often no larger than a city block, were assumed to be too small and too cold to generate any kind of magnetic activity. Yet, when researchers examined fragments of the asteroid Vesta, they found something impossible: tiny magnetic imprints frozen into the rock like a cosmic fingerprint. These traces suggest that, billions of years ago, this unassuming space rock had its own magnetic field, pulsing weakly but undeniably around it. How does a chunk of space debris without a molten core, the engine that powers Earth's magnetic field, manage this feat? The answer might lie in the chaos of the early solar system. Picture this: Vesta, one of the largest asteroids in the belt, wasn't always the cold, inert world we see today. In its youth, it was likely a molten protoplanet, its interior churning with heat from radioactive decay. For a brief window, that seething liquid metal core could have acted like a dynamo, spinning and generating a magnetic field just as Earth's does. Then, as Vesta cooled and solidified, the field vanished, but not before leaving behind magnetic echoes trapped in its minerals. But Vesta isn't the only asteroid hiding magnetic secrets. When Japan's Hayabusa mission retrieved samples from Itokawa, scientists discovered something even more puzzling. Certain grains were magnetized in ways that didn't match the surrounding rock. It's as if these tiny fragments were blasted with a magnetic pulse at some point in their history, possibly from a nearby asteroid collision or a close encounter with the sun's explosive flares. These findings suggest that magnetism in space isn't just a planetary trait. It's a dynamic, unpredictable force that can leave its mark even on the smallest bodies. The implications are profound. If asteroids once had magnetic fields, it means they were far more geologically active than we ever imagined. Some might have even had fleeting moments of molten cores, miniature versions of the processes that shape planets. That changes how we view these objects, not just as dead relics, but as worlds with hidden histories of transformation. Then there's the practical angle. Magnetic fields act like shields, deflecting solar radiation and cosmic rays. If some asteroids once had them, could they have protected organic molecules on their surfaces, preserving the ingredients for life in the void? It's a tantalizing thought, especially when paired with discoveries of water and amino acids on these same rocks. Suddenly, asteroids start to look less like barren wastelands and more like cosmic arcs, carrying and sheltering lives, building blocks across the ages. The biggest mystery, though, is how common these magnetic ghosts might be. With missions like Lucy and Psyche set to explore more asteroids in the coming years, we might uncover even more evidence of these vanished fields. Every new detection peels back another layer of the solar system's hidden story, revealing a past where even the smallest rocks had moments of planetary grandeur. And if we're lucky, the answers might just rewrite what we thought we knew about the birth of worlds. Some asteroids refuse to travel the cosmos alone. They come in pairs, locked in a silent dance that defies the solitude of space. These binary systems, where two asteroids orbit each other like cosmic partners, are among the most fascinating oddities in our solar system. Take Didymos and its tiny moon Dimorphos, for example. Didymos, a half-mile-wide rock, spins so fast it flings material into space, some of which coalesced into Dimorphos, a mere 500 feet across. Together, they form a miniature planetary system, a scaled-down version of Earth and the Moon drifting through the void. What makes these binary pairs so puzzling isn't just their existence, it's how they form in the first place. Unlike planets, which grow from swirling disks of gas and dust, binary asteroids often emerge from chaos. Some are born from catastrophic collisions, where a violent impact shatters a larger asteroid, leaving two fragments gravitationally bound. Others, like Didymos and Dimorphos, might spin so rapidly that material peels away from their surfaces, forming a second body. Then there's the Yorp effect, a quirky phenomenon where sunlight, unevenly absorbed and radiated by an asteroid's irregular shape, can nudge it into a spin fast enough to split it in two. But why does this matter beyond cosmic curiosity? Because binary systems are the ultimate test labs for planetary defense. In 2022, NASA, a DART mission slammed into Dimorphos at over 14,000 miles per hour, not just for spectacle, but to see if we could alter an asteroid's orbit. The results were staggering. Dimorphos' path around Didymos shrank by 32 minutes, proving that with enough force, we might one day nudge a threatening asteroid off a collision course with Earth. These paired asteroids also offer clues about the solar system's violent past. Their orbits, shapes, and compositions are like forensic evidence, revealing the forces that shape them. Studying binaries helps us understand how asteroids fracture, reform, and interact, painting a clearer picture of the chaos that once ruled the early solar system. Yet the biggest mystery remains: how many of these duos are out there? Before space telescopes and radar imaging, we assumed binaries were rare. Now, we know they're surprisingly common, especially among near-Earth asteroids. Some even come in triple systems, with one asteroid hosting two smaller companions. As missions like ESA's Hera prepare to visit Didymos and Dimorphos post-impact, we're on the verge of unlocking even more secrets. These celestial partnerships aren't just scientific novelties, they're keys to understanding everything from planetary formation to our own survival. And in their silent, spinning embrace, they remind us that even in the vast emptiness of space, nothing is ever truly alone. The surface of Asteroid Bennu looks solid from afar, but the moment NASA OSIRIS-REx spacecraft tried to touch down, it nearly sank straight through, like stepping onto a snowdrift only to plunge waist-deep. This surreal moment revealed one of the solar system's weirdest asteroid secrets. Many of these space rocks aren't solid at all. They're rubble piles, loose collections of boulders, pebbles, and dust barely held together by gravity, more akin to a cosmic bag of marbles than a single, sturdy object. Bennu, for instance, is so porous that an estimated 40% of its volume is empty space. If you stood on its surface, you might hear the rocks beneath you shifting and settling like a landslide in slow motion. This flimsy structure isn't just a quirky detail, it's a fundamental rethinking of what asteroids are. Traditionally, we imagine them as fractured but coherent chunks of planetary debris. Now, we know some are more like gravitational jigsaw puzzles assembled from the fragments of ancient collisions. Every time two asteroids smash together, the debris doesn't just vanish, it can clump back together over millennia, forming a new, shaky conglomerate. Bennu, Ryugu, and even the infamous asteroid Itokawa all share this fragile architecture, suggesting rubble piles might be the rule, not the exception. For spacecraft missions, this poses a nightmare scenario. Landing on a rubble pile isn't like docking with a solid moon or planet. When OSIRIS-REx attempted to collect samples from Bennu, its robotic arm punched straight through the surface, sending rocks flying in all directions. The asteroid's feeble gravity, 100,000 times weaker than Earth's, couldn't even hold the debris down. Instead of a tidy scoop, the spacecraft found itself surrounded by a chaotic plume of ejected material, some of which orbited Bennu for days before drifting back down. Future missions will need entirely new strategies to navigate these unpredictable terrains, perhaps using harpoons, nets, or even gentle hover and kiss techniques to avoid triggering an avalanche. The implications stretch beyond engineering headaches. Rubble piles might hold the key to understanding how planets form. In the early solar system, similar loose aggregations of rock and ice likely served as the building blocks for worlds like Earth. By studying Bennu's fragile structure, we're essentially peering back in time to witness the infant stages of planetary assembly. But there's a darker twist. Rubble piles are also cosmic time bombs. Their weak cohesion means they're more likely to fracture under stress, whether from a passing planet's gravity or even sunlight pressure. Some scientists speculate that near-Earth asteroids like Bennu could eventually disintegrate entirely, scattering their debris across the solar system or even raining smaller fragments down on our planet. Yet the biggest mystery remains: how do these piles stay intact at all? With so little gravity and no adhesive force beyond weak van der Waals interactions between dust grains, they shouldn't survive the solar system's harsh environment. One theory suggests static electricity, generated by the constant bombardment of solar radiation, might help bind particles together. Another proposes that micrometeorite impacts act like a cosmic hammer, compacting the surface just enough to create a fragile crust. Every new mission to a rubble pile asteroid seems to uncover more questions than answers. proving that even the flimsiest space rocks can be surprisingly resilient. So the next time you picture an asteroid, don't imagine a monolithic mountain in space. Think of it instead as a precarious house of cards held together by the faintest whisper of gravity, a testament to the universe's ability to build complexity from chaos. And as we send more probes to these enigmatic heaps, one thing's certain: the solar system's quietest rocks still have the loudest stories to tell. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations, an object unlike anything we'd seen before. Named Oumuamua, Hawaiian for scout, this visitor wasn't just another asteroid or comet. It was the first confirmed interstellar traveler, a guest from another star system passing through our cosmic neighborhood. But what made Oumuamua truly bizarre wasn't just its origin, it was its shape. Most asteroids and comets are roughly spherical or lumpy. Oumuamua, however, was elongated, stretching up to 800 meters long while barely a tenth as wide, like a cosmic cigar tumbling silently through space. The anomalies didn't stop there. Unlike comets, which typically sprout glowing tails of gas and dust when warmed by the sun, Oumuamua showed no visible outgassing, yet it accelerated slightly, as if something unseen were pushing it. This unexpected behavior sparked heated debates. Some scientists argued it might be a rare type of dark comet, emitting invisible gases that nudged it forward. Others proposed even wilder ideas, like Harvard astrophysicist Avi Loeb, who suggested Oumuamua could be artificial, a solar sail or debris from an alien civilization drifting between the stars. The natural explanation isn't any less strange. One theory posits that Oumuamua might be a shard of a larger body torn apart by tidal forces near its home star, leaving behind this eerie, needle-like fragment. Another suggests it's a frozen hydrogen iceberg, a type of object so exotic it's never been observed before. Hydrogen ice, if it exists, could explain the acceleration without visible outgassing, since hydrogen evaporates invisibly in sunlight. But here's the catch: we may never know for sure. Oumuamua is already racing out of the solar system, too distant for further study with current technology. Its brief visit left us with more questions than answers, a tantalizing glimpse into how little we understand about what lurks between the stars. What makes Oumuamua so revolutionary isn't just its mystery, it's the door it opened. Before its arrival, astronomers assumed interstellar visitors would be vanishingly rare. Now we've spotted a second one, Comet Borisov, and estimates suggest there could be thousands passing through the solar system at any given moment. Each of these cosmic vagabonds carries clues about the diversity of planetary systems beyond our own, hinting at processes and materials we've never encountered. The controversy over Oumuamua's nature forces us to confront a humbling truth. Space is far stranger than our textbooks suggest. Whether it's a shredded planet fragment, an alien artifact, or something entirely new, this interstellar scout reminds us that the universe is full of surprises, and the next one might be even harder to explain. Asteroids have always been considered silent, lifeless rocks until scientists started detecting something completely unexpected: pockets of volatile gases seeping from their surfaces. These aren't just traces of inert material. We're talking about nitrogen, carbon dioxide, and even methane, gases that usually signal geological or biological activity. The discovery raises a startling question. How can these tiny, frozen worlds, billions of miles from the warmth of the sun, still be exhaling gases as if they're alive? Take the asteroid Bennu, for example. When NASA OSIRIS-REx spacecraft studied it up close, it didn't just find water ice and organic molecules. It observed faint plumes of gas erupting from the surface like tiny geysers in the void. These weren't massive eruptions, but delicate puffs of vapor, likely released when sunlight warmed pockets of volatile material trapped just beneath the asteroid's rocky skin. Similar emissions have been spotted on other asteroids, including Ceres, where the Dawn mission detected water vapor escaping from mysterious bright spots. So where do these gases come from? One theory points to ancient reservoirs locked inside the asteroid since the birth of the solar system. Imagine these space rocks as cosmic freezers, preserving volatile compounds in their icy interiors for billions of years. Over time, micrometeorite impacts or solar heating could fracture the surface, opening tiny vents that allow these trapped gases to escape. But there's another, more tantalizing possibility. Some asteroids might still be geologically active, with hidden processes churning beneath their surfaces. This isn't as far-fetched as it sounds. On Ceres, those bright spots turned out to be deposits of sodium carbonate, a mineral often formed when liquid water interacts with rock. The presence of vapor plumes suggests that even now, Ceres might have pockets of briny water slowly evaporating into space. If true, it means some asteroids aren't just frozen relics. They could be dynamic worlds with subsurface chemistry humming along, even in the absence of a traditional heat source. Then there's the methane mystery. On Earth, methane is often associated with life, though it can also form through geological processes. When traces of it were detected on asteroids like Ryugu, scientists had to consider both possibilities. Could it be a remnant of some long-dead organic process, or just another product of cosmic chemistry? Either way, these gases challenge our assumptions about how complex these simple space rocks really are. The implications ripple outward. If asteroids can retain and release volatile gases, they might have played a bigger role in delivering key ingredients to early Earth than we thought. Nitrogen, for instance, is essential for life as we know it, and finding it on asteroids suggests they could have been cosmic couriers, ferrying these elements to our planet during its formative years. But the real puzzle is how these gases persist at all. Space is a relentless environment where solar radiation and extreme temperatures should have stripped asteroids of such delicate materials eons ago. Yet here they are, defying expectations. Some researchers think organic-rich asteroids might act like sponges, absorbing and protecting volatiles within their porous structures. Others speculate that certain gases could be reforming continuously through chemical reactions between minerals and cosmic rays, creating a slow but steady supply. Every new discovery peels back another layer of the asteroid enigma. What we once dismissed as barren, unchanging rocks are now revealing themselves as dynamic, even temperamental worlds, quietly exhaling secrets into the void. And as we keep searching, one thing's clear: the universe has a knack for hiding its most fascinating stories in the most unexpected places. If there's one thing asteroids have taught us, it's that nature has a flair for the dramatic, especially when it comes to shapes. Forget the dull, potato-like lumps we often imagine. Some of these space rocks look like they've been sculpted by an avant-garde artist. Take Cleopatra, an asteroid so bizarre it's earned the nickname Dog Bone in space. This metallic oddball stretches over 160 miles long but pinches inward at its center, giving it the unmistakable silhouette of a cosmic dumbbell. Then there's Arrokoth, the most distant object ever visited by a spacecraft, which resembles a flattened snowman made of two pancakes glued together. These aren't just quirks of space, they're cosmic conundrums that force us to rethink how asteroids form and evolve. Cleopatra's peculiar shape, for instance, shouldn't exist under standard formation models. Most asteroids are thought to clump together from smaller fragments, creating lumpy but roughly symmetrical bodies. But Cleopatra's narrow waist suggests something far more violent, a catastrophic collision that nearly tore it apart, leaving behind this twisted metallic relic. Radar observations reveal it's not alone either. The asteroid spins so fast once every 5 hours that it's likely flinging material into space, possibly even spawning tiny moons. This raises a startling possibility. Some asteroids might not just be static rocks but dynamic factories, constantly reshaping themselves and their surroundings. Arakoth, on the other hand, tells a different story. Located in the Kuiper belt, this bi-lobed object looks like two separate bodies gently merged in slow motion. Its smooth, untouched surface hints that it's a pristine remnant of the solar system's earliest days, a time when dust grains stuck together in low-speed collisions to form these contact binaries. The absence of impact craters suggests Arakoth has been chilling in deep freeze for billions of years, untouched by the chaos that reshaped asteroids closer to the Sun. What makes these shapes so revolutionary is the way they defy our expectations. Traditional models assumed asteroids formed through chaotic, high-energy smash-ups, leaving them scarred and asymmetrical. But Arakoth's delicate structure proves some objects assembled gently, like snowflakes drifting together in the void. Meanwhile, Cleopatra's extreme form shows that even after formation, asteroids can undergo radical transformations, warping into shapes that seem almost impossible. And then there's the practical puzzle. How do these fragile structures hold together? Cleopatra's thin neck should snap under its own spin, and Arakoth's two lobes seem precariously balanced. Some scientists think static electricity or weak van der Waals forces might help bind them, while others speculate that their unusual shapes actually stabilize them, like a spinning coin that stays upright as long as it's in motion. Every new image of these misshapen asteroids peels back another layer of mystery. They're not just rocks, they're time capsules preserving the violent, delicate, and downright weird processes that built our solar system. And with missions like Lucy set to explore more Trojans in Jupiter's orbit, who knows what other cosmic sculptures we'll find? One thing's certain, the universe's creativity knows no bounds, and the strangest shapes might still be waiting, hidden in the dark. One of the strangest behaviors scientists have caught asteroids doing is something that seems impossible at first glance, changing color right before our eyes. Take Phaethon, the bizarre blue asteroid responsible for the annual Geminid meteor shower. When astronomers observed it over time, they noticed something unsettling. It wasn't staying the same hue. This space rock, which should have been a static shade of gray like most asteroids, was actually shifting toward a deeper red. At first, researchers thought it might be a trick of the light or an error in observation. But the data was undeniable. Phaethon was undergoing a real physical transformation, and the implications were staggering. So what's turning these asteroids into cosmic chameleons? The prime suspect is the Sun's relentless radiation. Asteroids like Phaethon spend their lives baking in solar energy, with no atmosphere to shield them from ultraviolet light and charged particles. Over time, this radiation can literally cook the surface, altering the chemical composition of minerals in a process called space weathering. Think of it like leaving a piece of paper in the sun. It fades and yellows as the UV rays break down its molecules. But in space, the effects are even more extreme. Certain minerals, especially those rich in iron or organic compounds, darken or redden as radiation blasts away their outer layers, exposing fresh material beneath. But here's where Phaethon throws a curveball. Most weathered asteroids get darker, but this one is getting redder. One theory suggests it's shedding tiny dust particles from its surface, leaving behind a freshly exposed layer that hasn't yet been fully sunburned. Another idea points to thermal fracturing. The asteroid's wild temperature swings, from scorching highs to cryogenic lows, could be cracking its surface like an old sidewalk, revealing pristine rock underneath. And then there's the most tantalizing possibility. Phaethon might be so active, with dust and gas escaping its surface, that it's essentially repainting itself in real time. This isn't just a Phaethon quirk either. Other asteroids like Bennu have shown similar, if subtler, color shifts. Data from OSIRIS-REx revealed patches where the surface appeared both freshly exposed and heavily weathered, suggesting Bennu's complexion is in constant flux. Even more puzzling, some asteroids change color temporarily when they pass close to the Sun, like cosmic mood rings reacting to heat. The implications go beyond mere curiosity. If asteroids can change color, it means our assumptions about their composition might be flawed. A reddish asteroid could be misinterpreted as carbon-rich when, in reality, it's just sunburned. That's a big deal for missions like Hayabusa 2 or OSIRIS-REx, which rely on pre-landing observations to select sampling sites. Imagine showing up to what you thought was a mineral-rich asteroid, only to find it's just a weathered shell disguising its true nature. And then there's the bigger cosmic mystery. If space weathering happens this fast on asteroids, could it affect other bodies like Mars's moons or distant Kuiper belt objects? Are we underestimating how quickly the solar system's smallest members evolve under the sun's harsh glare? Every color-changing asteroid we find forces us to rethink the lifespan and stability of these objects, proving that even in the frozen reaches of space, nothing stays the same for long. So the next time you hear about an asteroid shifting hues, remember, it's not just an oddity, it's a sign that the universe is far more dynamic than we ever imagined, where even the quietest rocks are slowly transforming under the relentless touch of starlight. Asteroids aren't just lone wanderers, some of them are busy building their own miniature solar systems. Scientists have spotted a handful of these space rocks surrounded by swirling disks of debris, not unlike the rings of Saturn or the dusty clouds where planets are born. The most striking example, asteroid Chariklo, a 250-mile-wide body orbiting between Saturn and Uranus, which stunned astronomers when they discovered it had not one, but two thin, glittering rings encircling it. This wasn't just a curiosity, it was a revelation. If something as small as an asteroid could harbor its own ring system, what other cosmic rules were we missing? The parallels to planet formation are impossible to ignore. In the early solar system, dust and gas coalesced into disks around young stars, eventually clumping together to form planets. Chariklo's rings suggest asteroids might undergo a scaled-down version of this process, where debris in orbit could slowly accumulate into tiny moons. We've even seen this in action with asteroids like Didymos, which spun so fast it shed material to form its moonlet, Dimorphos. But rings take the phenomenon a step further. They're evidence of a delicate balancing act, where gravity, rotation, and collisions all conspire to create something fleeting and beautiful in the void. What's truly baffling is how these rings persist at all. Chariklo's rings, for instance, are narrow and well-defined, almost like cosmic racetracks. Normally, such structures should dissipate within a few centuries, their particles scattering or clumping into moons. The fact that we can see them means they're either being actively replenished, perhaps by ongoing collisions or eruptions of subsurface material, or they're being sculpted by unseen shepherd moons, tiny bodies whose gravity herds the debris into neat bands. Then there's the mystery of origin. Did Chariklo's rings form when a smaller asteroid smashed into it, launching debris into orbit? Or could they be remnants of a catastrophic breakup where a larger body fractured and left behind these ghostly loops? The answer might lie in another bizarre asteroid, Chiron, which also shows hints of a ring system. Chiron behaves like a hybrid between an asteroid and a comet, occasionally sprouting jets of gas and dust. If its rings are fed by these eruptions, it would mean some asteroids are far more geologically active than we ever imagined, puffing out material like cosmic steam engines. The implications stretch beyond mere spectacle. If asteroid debris disks are common, they could be cosmic nurseries for miniature moons, some no larger than a house. These moonlets, in turn, might hold clues about how planets like Earth got their satellites. Did our own moon form from a similar disk of debris after the giant impact that created it? Asteroids with rings offer a scaled-down laboratory to test these ideas, letting us observe processes that would be impossible to see around full-sized planets. But the real surprise came when researchers realized these rings might not be static. Simulations suggest that over time, the debris could coalesce into fully formed moons, transforming the asteroid into a binary system. That means we might be catching these space rocks in the act of creating their own companions, a slow-motion dance that could take millions of years. It's a humbling reminder that even the smallest objects in the solar system are dynamic, evolving worlds, not just frozen relics of the past. So the next time you picture an asteroid, don't just imagine a lonely boulder adrift in space. Think of it as a potential architect spinning out rings and moons in a quiet corner of the cosmos. These tiny, intricate systems prove that the universe doesn't need vast scales to create something extraordinary sometimes. All it takes is a modest rock and the right conditions to start building all over again. Among the countless scars left on asteroids over billions of years, some stand out as particularly violent hypervelocity impacts, crashes so powerful they don't just leave craters but transform the very fabric of these space rocks. Picture a collision so fast, so brutal, that the energy released doesn't just shatter the surface. It vaporizes rock on contact, creating temperatures hotter than lava and pressures rivaling the center of the Earth. These aren't your average asteroid bumps. They're cosmic cannon fire, and the bizarre mineral formations they leave behind are rewriting what we know about the chaos of the early solar system. Take the asteroid Vesta, for example. When NASA's Dawn spacecraft mapped its surface, it found vast plains of once molten rock, frozen in time like a geological snapshot. These weren't formed by volcanic activity, but by impacts so intense they liquefied the surface instantly, creating temporary impact seas that flowed before rapidly cooling into glassy, otherworldly landscapes. Even more striking were the patches of shocked minerals, quartz and olivine crystals, warped by pressures so extreme their atomic structures bent into configurations never seen on Earth. Then there's the mystery of the melt veins. Some asteroids, like the one that carved Meteor Crater in Arizona, contain thin streaks of once molten material threading through their interiors like cosmic lightning bolts. These veins are the fingerprints of hypervelocity strikes, where shockwaves traveled through the rock fast enough to melt narrow channels without fully destroying the surrounding structure. It's like cracking a whip so hard it turns the air into plasma, a fleeting moment of violence preserved in stone. What makes these impacts truly bizarre isn't just their destructive power, but their creative potential. Under normal conditions, certain minerals take millions of years to form. But in the split-second chaos of a hypervelocity collision, chemistry gets turned on its head. Diamonds can crystallize instantly from carbon-rich asteroids. Rare metals alloy in ways impossible under gentle conditions. Some scientists even speculate that these impacts could have synthesized complex organic molecules, potentially seeding the building blocks of life across the solar system. Yet the most puzzling discoveries come from the aftermath. On asteroids like Itokawa, researchers found impact spherules, tiny, perfect beads of glass scattered across the surface. These aren't debris from the impactor but droplets of the asteroid itself, flung into space by the collision only to rain back down and solidify into delicate orbs. It's as if the asteroid momentarily wept molten tears before freezing them in the vacuum. The implications stretch far beyond asteroids. If hypervelocity impacts can reshape surfaces, forge new minerals, and even spark chemistry, they might have played a hidden role in shaping planets. Earth's own crust could bear similar scars from its violent youth, long since erased by erosion and plate tectonics. Asteroids, with their frozen impact records, give us a window into processes we can't witness anywhere else, a reminder that sometimes the most profound changes come from the fastest, fiercest moments in time. And perhaps the strangest twist, these collisions might still be happening today. With millions of asteroids zipping through the solar system, hypervelocity strikes could be transforming surfaces right now in real time. Every new crater we find isn't just a mark of destruction, it's a laboratory of cosmic alchemy, where the universe turns chaos into something extraordinary. Most asteroids are content to drift silently through space, unchanging for eons, but a rebellious few refuse to play by the rules. Enter the active asteroids, cosmic renegades that blur the line between asteroid and comet by suddenly spewing plumes of dust or gas into the void. Take 311P/Pan-STARRS, a space rock that stunned astronomers when it sprouted not one, but 6 distinct dust tails fanning out like a celestial peacock. This wasn't some icy comet warming near the sun, it was a stony asteroid, the kind that should have been completely inert. So why was it suddenly vomiting enough material to form a 70,000-mile-long debris field? The answer might rewrite how we classify these objects. Active asteroids like Pan-STARRS behave like cosmic chameleons, masquerading as ordinary rocks until something triggers their outburst. Some, like asteroid 238P/Reed, eject water vapor when solar heating cracks their interiors, exposing hidden ice. Others, like 647-8 Gault, literally crumble before our eyes, spinning so fast they fling surface material into space like a dog shaking off water. Then there's the baffling case of asteroid 324,000 Phaethon, which somehow generates the Geminid meteor shower despite lacking the icy reservoir of a typical comet. These aren't just oddballs, they're forcing us to confront a fundamental question. What really makes an asteroid an asteroid? The debate hinges on composition. Traditional thinking says asteroids are dry, rocky leftovers from planet formation, while comets are icy time capsules from the solar system's outer edges. But active asteroids smash that binary. 311P's multiple tails suggest it's not just passively shedding dust, something inside is actively fragmenting, possibly due to built-up stresses or volatile gases punching through its crust. Infrared scans reveal its surface is scorching hot, baked by the sun to temperatures that might be literally cracking it apart. Meanwhile, spectroscopic studies of other active asteroids show traces of minerals like serpentine, which forms in the presence of water. Suddenly, the line between rocky asteroid and icy comet looks suspiciously blurry. One radical theory suggests these objects could be rock comets, asteroids packed with subsurface ices that occasionally erupt when disturbed. Another proposes there the shattered remains of larger bodies, their fractured interiors still venting trapped gases billions of years after their destruction. There's even speculation that some might be camouflaged comets, their outer layers baked into a rocky crust that hides an icy heart. Every new discovery adds another twist. The Lucy mission recently spotted asteroid 1527-1261, Donald Johanson ejecting plumes during its approach to Jupiter, proving activity isn't confined to the inner solar system. What makes these active asteroids so thrilling is their unpredictability. Unlike comets, which become active predictably as they near the sun, these space rocks erupt seemingly at random. One day they're quiet, the next they're flinging debris at speeds over 22 miles per hour, fast enough to escape their minuscule gravity forever. This volatility makes them both a scientific goldmine and a navigation hazard. When Japan's Hayabusa 2 approached asteroid Ryugu, it had to dodge unexpected pebble ejections that could have damaged the spacecraft. Future missions might need to treat all asteroids as potential powder kegs, capable of spontaneous outbursts without warning. Yet the biggest mystery remains: how many of these imposters are lurking undetected? Current estimates suggest at least 1 in every 1,000 asteroids could be active, meaning our solar system might be teeming with these cosmic tricksters. Each one we find forces us to rethink the asteroid-comet divide, proving that nature rarely fits into our neat categories. As observation techniques improve, we might discover that activity isn't the exception but a hidden rule, a secret life of asteroids we're only beginning to decode. So the next time you hear about an asteroid acting out, remember, it's not misbehaving, it's revealing just how little we truly understand about these nomadic space rocks and the dynamic, ever-changing solar system they call home. Among the most profound discoveries on asteroids are the chemical ingredients that make life possible, not just simple organic molecules, but the specific building blocks of biology itself. We're talking about amino acids, sugars, and even nucleobases, the very compounds that form proteins, RNA, and DNA. These aren't just scattered randomly, they're arranged in ways that mirror the probiotic chemistry thought to have sparked life on Earth. Take the Murchison meteorite, a chunk of asteroid that fell to Australia in 1969. When scientists analyzed it, they found over 90 different amino acids, including many that aren't even used by life on Earth. This wasn't contamination, it was proof that space is quietly, relentlessly cooking up the raw materials for life. What makes these discoveries so revolutionary isn't just the presence of these molecules, but their complexity. On asteroids like Ryugu and Bennu, missions have detected ribose, the sugar backbone of RNA, alongside uracil, one of the 4 nucleobases essential for genetic coding. These compounds aren't forming in warm tidal pools or deep sea vents like we once imagined. They're assembling in the freezing vacuum of space, on rocks bombarded by radiation and devoid of liquid water. It's like walking into an empty kitchen and finding a 5-course meal miraculously prepared with no chef in sight. This cosmic pantry forces us to confront the panspermia hypothesis, the idea that life's precursors might have hitched rides on asteroids, seeding planets like Earth with the tools to build biology. The math is startlingly plausible. Over billions of years, trillions of asteroids have crisscrossed the solar system, colliding with young worlds and depositing their organic cargo. Some estimates suggest Earth could have received as much as 50,000 tons of probiotic material annually during its early history. That's not just a sprinkle of ingredients, it's a downpour of potential. But here's where it gets even stranger. These molecules aren't just surviving in space, they're evolving. Experiments simulating asteroid conditions show that cosmic rays can actually drive simple organics toward greater complexity, forging chemical bonds that resist the harsh environment. On carbon-rich asteroids, ultraviolet light and radiation might act like a cosmic chemist, shuffling atoms into ever more sophisticated arrangements. Some researchers believe certain asteroids could have functioned as primitive laboratories, where simple molecules linked into chains, forming protoproteins or RNA like polymers long before they reached a planet. The implications are staggering. If life's building blocks are this widespread, then the universe might be primed for biology wherever conditions allow. It's not that asteroids are carrying life itself, but they're certainly delivering the instruction manual. Every new sample we pull from these space rocks adds another page to that manual, revealing a story where life isn't a miraculous fluke, but an inevitability written into the fabric of the cosmos. Yet the biggest mystery remains unanswered. How close did these asteroids come to crossing the line from chemistry to biology? Did they ever host reactions sophisticated enough to edge toward something alive? With missions like OSIRIS-REx and Hayabusa 2 bringing back pristine samples, we're closer than ever to knowing whether the universe's recipe for life is simple, redundant, or still hiding secrets we've yet to uncover. Imagine a cosmic treasure chest drifting through space, its surface shimmering with enough metal to dwarf Earth's entire supply. This isn't science fiction. It's asteroid Psyche, a massive, potato-shaped world made almost entirely of nickel and iron, orbiting between Mars and Jupiter. But Psyche isn't just a curiosity. It's a time capsule offering an unprecedented glimpse into the violent hearts of planets. Most rocky worlds, including Earth, bury their metallic cores under miles of crust, forever out of reach. Psyche, though, appears to be the exposed skeleton of a failed planet, a naked core stripped bare by ancient collisions. Studying it could rewrite what we know about planetary formation and unlock riches beyond imagination. The sheer abundance of metal on Psyche is staggering. Radar observations suggest its composition is roughly 90% metallic, with traces of silicate rock sprinkled like seasoning. For scale, if mined, its iron alone could supply Earth's needs for millions of years. But the real jackpot lies in rarer metals like platinum, gold, and cobalt, which tend to bond with iron in planetary cores. Private companies like Astroforge and Planetary Resources are already eyeing near-Earth metallic asteroids, testing extraction technologies that could one day turn these space rocks into cosmic gas stations or off-world factories. Yet the scientific value of Psyche might outweigh even its mineral wealth. By analyzing its surface, we're essentially dissecting a planetary core without the need to drill through thousands of miles of rock. Early solar system models suggest molten metal cores generate magnetic fields critical for shielding life from radiation. Psyche's magnetism, or lack thereof, could reveal whether small bodies like it ever had protective fields, hinting at conditions that might have nurtured early life elsewhere in the cosmos. Here's the twist: Psyche might not be alone. Observations reveal entire families of metallic asteroids, like 16 Psyche's namesake group, hinting at a shattered protoplanet whose fragments now litter the asteroid belt. Some, like asteroid Cleopatra, even seem to be loosely held rubble piles of metal. Imagine a dog-bone-shaped hunk of iron held together by little more than gravity. These metallic oddballs challenge our assumptions about how asteroids form and evolve, suggesting some may have been forged in the furnaces of ancient collisions that liquefied entire worlds. But mining these cosmic lodes won't be easy. Metallic asteroids are incredibly dense. Landing a spacecraft on Psyche would feel like parking on a giant ball bearing. Their high reflectivity also means scorching daytime temperatures, while the lack of loose regolith makes anchoring drills a nightmare. Some proposals involve using solar mirrors to focus sunlight, melting surface metal into collectible streams, a space-age version of panning for gold. Others favor robotic scouts that could identify rich veins before larger operations begin. The bigger question isn't just how we'll mine them, but what happens when we do. A single metallic asteroid could flood markets, destabilizing global economies. That's prompted early discussions about cosmic resource laws, with groups like the United Nations proposing frameworks to avoid extraterrestrial gold rushes. Meanwhile, scientists caution against viewing these asteroids purely as commodities. Their untouched surfaces are history books written in atomic structures, holding clues to everything from Earth's core to the origins of the solar system. Psyche's upcoming mission, launching soon, aims to peel back these layers of mystery. The spacecraft will map its surface, measure its composition, and hunt for signs of ancient magnetism. Every new crater it studies could be a window into the asteroid's violent past, while strange mineral formations might reveal processes we've never witnessed. Metallic asteroids aren't just curiosities or cash cows, they're bridges between the known and the unimaginable. Whether as future mines or planetary autopsy subjects, they remind us that the solar system's most valuable treasures aren't always the ones that glitter. Sometimes they're the ones that tell us how the universe forges its wonders in the first place. Some of the most haunting features on asteroids aren't what you can see, but what you almost can't. Scattered across these space rocks are faint, ghostly impressions of ancient violence, impact craters so eroded they've nearly vanished. These ghost craters are the solar system's pale scars, hints of collisions that happened billions of years ago, smoothed over by time but never fully erased. On asteroids like Bennu and Vesta, these phantom pits tell a story of constant reinvention, where surfaces are reshaped not by wind or water, but by forces far stranger. Take Bennu's mysterious shallow depressions, wide, dish-like features that lack the sharp edges of fresh craters. These aren't just weathered pits, they're evidence of a phenomenon called impact gardening. Over eons, smaller meteorites bombard the asteroid, churning its surface like a cosmic tiller. The loose rubble pile structure allows impacts to send shockwaves that redistribute material, slowly filling in older craters until only a faint shadow remains. It's as if the asteroid has a memory, holding onto the echoes of its past trauma even as it buries them. But ghost craters aren't just about erosion, they're clues to an asteroid's hidden activity. On Ceres, Dawn spacecraft images revealed circular patterns of fractures and mineral deposits where massive impacts once struck. The craters themselves are long gone, but their fingerprints linger in the way the dwarf planet's crust cracked or pooled with briny residue. Some scientists believe these ghostly outlines mark places where subsurface ice briefly melted from the impact heat, then refroze into new geological formations. That means these faded scars aren't just passive relics, they're snapshots of moments when asteroids briefly awakened, their interiors responding dynamically to outside forces. Then there's the puzzle of Vesta's ghost basins. This asteroid, one of the largest in the belt, bears the faint remains of titanic collisions, so massive they should have shattered it entirely. Yet the scars are barely visible, smoothed by a process called viscous relaxation. Vesta's crust, heated by radioactive decay in its youth, behaved less like solid rock and more like thick syrup, slowly oozing to fill in the colossal wounds over millions of years. It's a reminder that even asteroids have a kind of geology, with materials that flow, crack, and heal in ways we're only beginning to understand. The most startling implication. Ghost craters suggest asteroids are far more dynamic than they appear. A fresh, crisp crater might tell you about a single impact, but a ghost crater tells you about everything that's happened since the countless micrometeorite strikes, the seismic shaking from nearby collisions, even the subtle push of sunlight altering the surface grain by grain. They're like cosmic clocks, their fading edges hinting at the age and activity level of the asteroid. On Bennu, the prevalence of ghost craters helped scientists estimate its surface is surprisingly young, constantly recycling itself on timescales of just a few million years. Yet for all they reveal, ghost craters also hide secrets. Why do some asteroids like Itokawa show almost no signs of them while others are littered with these half-remembered wounds? Could it be differences in composition, internal heat, or even the angle at which they were struck? Every mission that maps an asteroid's surface adds another piece to this puzzle, proving that even the faintest marks can hold the loudest stories. So the next time you see an asteroid image, look closely. Those barely their circles and smudged depressions aren't flaws in the data. They're whispers from the past, proof that in space, even the quietest rocks never stop changing. And as we keep searching, who knows what other ghosts we'll uncover, silently testifying to the violence and beauty of the solar system's history. The sun doesn't just light up the solar system, it etches its signature onto every surface it touches, and asteroids bear some of the most bizarre proof. Solar wind, that relentless stream of charged particles racing outward from the sun at nearly 1 million miles per hour, doesn't just pass harmlessly over these space rocks. It transforms them, leaving behind ghostly imprints that scientists call space weathering. Picture an asteroid's surface as a cosmic canvas, constantly being repainted by invisible brushes of protons and electrons. Over millennia, this silent bombardment darkens minerals, alters chemical bonds, and even creates nanoscale metallic blobs that shouldn't exist in nature. These aren't just passive changes, they're active rewritings of an asteroid's story, making fresh surfaces look ancient and turning simple rocks into time capsules of solar fury. One of the strangest effects happens to olivine, a common mineral in asteroids. Under the microscope, solar wind bombardment doesn't just scratch its surface, it shatters the crystal structure at an atomic level, leaving behind a shattered, glassy layer called a rim. These rims, sometimes only a few hundred atoms thick, are like the asteroid's version of a sunburn, recording every moment of exposure. The more weathered the rim, the longer the asteroid has been exposed to the solar wind's relentless sandblasting. But here's the twist, this damage isn't uniform. Asteroids spinning rapidly might have one side heavily weathered while the other stays pristine, like a cosmic rotisserie chicken slowly charring under an open flame. Then there's the mystery of the nanophase ion. Solar wind doesn't just break minerals down, it rebuilds them in ways that defy earthly chemistry. When the wind's high-energy particles smash into iron-rich minerals, they knock atoms loose, some of which then clump together into microscopic pure iron beads. These nanoscale spheres, utterly alien to natural geology on Earth, scatter across the asteroid's surface like cosmic glitter. Their presence is a telltale sign of solar wind weathering, and they've been found on everything from lunar soil to asteroid Itokawa's grains. What's baffling is how these tiny iron beads persist at all. In Earth's oxygen-rich environment, iron rusts instantly, but in the vacuum of space, they remain pristine, metallic fingerprints of the sun's invisible handiwork. The implications ripple far beyond academic curiosity. Space weathering is the ultimate cosmic disguise, making fresh asteroid surfaces appear older than they are. That's a huge problem for missions like Hayabusa 2 or OSIRIS-REx, which rely on surface observations to select sampling sites. A patch that looks pristine might actually be weathered, its original composition hidden under a solar-altered veneer. Scientists have even spotted asteroids where weathering has created a bizarre optical illusion, surfaces that darken and brighten depending on the angle of sunlight, like some kind of celestial mood ring. But the real jaw-dropper, solar wind, might be the reason we've underestimated water in the solar system. When the wind's protons' hydrogen nuclei slam into oxygen-rich minerals on an asteroid, they can bond to form water molecules right on the surface. This process, called sputter deposition, means even bone-dry asteroids could be covertly manufacturing tiny amounts of water, molecule by molecule. Suddenly, the line between wet and dry asteroids blurs, suggesting the solar system might be far more hydrated than we ever imagined. Every weathered surface we study is a testament to the sun's quiet power, a reminder that even in the stillness of space, nothing stays untouched. The solar wind's etchings might be invisible to the naked eye, but they're rewriting our understanding of asteroids one atomic collision at a time. Some asteroids don't spin gracefully like tops. They tumble through space like drunken acrobats, flipping and twisting in ways that defy logic. Take asteroid Tautotes, a jagged, peanut-shaped rock that doesn't just rotate, it pirouettes along two different axes simultaneously, tumbling so chaotically its poles never point the same direction twice. If you stood on its surface, the horizon would lurch unpredictably, the sun rising and setting in different spots with no rhythm, like a cosmic funhouse mirror. This isn't just an oddity, it's a violation of everything we thought we knew about celestial mechanics. The secret behind this madness, gravity's invisible hand playing tricks. Most asteroids spin smoothly because their mass is evenly distributed, like a well-balanced wheel. But Tautotes and other tumblers like it are cosmic misfits. Their irregular shapes create uneven gravitational pulls, turning their rotations into a wobbly mess. Imagine trying to spin a lopsided potato in zero gravity. It wouldn't rotate cleanly but flop around in unpredictable directions. Tautotes takes this to extremes, with its two lobes acting like mismatched counterweights, tugging against each other in a never-ending struggle for stability. Then there's the Yorp effect. Yes, it's a real term short for the Yarkovsky-O'Keefe-Radzevsky-Ipadak effect. This mouthful describes how sunlight, striking an asteroid's uneven surface, can nudge it into increasingly erratic spins over millennia. Tiny photons might seem insignificant, but over billions of years, their collective push can torque an asteroid into a tumbling frenzy, especially if it's shaped like a jagged rock pile. Some asteroids, like Bennu, show signs of this slow-motion transformation, their rotations accelerating so much they might eventually fling material into space or even split in two. But the real shocker is how these tumblers defy destruction. Conventional wisdom says such chaotic motion should tear an asteroid apart, yet Tautotes has survived for billions of years. Its secret might lie in its rubble pile structure, a loose collection of boulders that absorbs the chaotic energy like a cosmic stress ball, flexing instead of fracturing. This resilience hints that many more asteroids could be tumbling in secret, their erratic rotations hidden until close observation reveals their dance. What's at stake isn't just celestial curiosity. Understanding these motions is crucial for spacecraft missions. Try landing on an asteroid that's somersaulting unpredictably, and you've got a recipe for disaster. NASA upcoming missions are already accounting for these spins, proving that in space, even the simplest assumptions can crumble under the universe's love for chaos. So the next time you picture an asteroid, don't imagine a serene, spinning orb. Think of it as a cosmic dancer twirling recklessly through the void, a reminder that the universe never runs out of ways to surprise us. Asteroids aren't supposed to leave trails, or at least, that's what scientists thought until they spotted space rocks behaving like cosmic graffiti artists, spraying dust behind them like miniature comets. The first jaw-dropping example, asteroid Phaethon, the rock responsible for the Geminid meteor shower. Unlike comets which shed ice and dust as they near the sun, Phaethon is dry and rocky. Yet when it swings close to the sun, it erupts with enough dust to create one of the year's most dazzling meteor displays. This wasn't just a fluke, it was a revolution. If a bone-dry asteroid could mimic a comet, what other cosmic rules were we missing? The mystery only deepened with the discovery of more active asteroids, like 133P/Elst Pizarro. This bizarre object orbits in the asteroid belt but sprouts a tail of dust every time it reaches the point in its orbit closest to the sun. At first glance, it looks like a comet, but its composition is pure asteroid. No ice, no frozen gases. So where's the dust coming from? The leading theory points to subsurface fractures. As sunlight heats the asteroid, thermal stress cracks its surface, releasing trapped dust and gas in silent, sun-powered eruptions. It's like squeezing a stress ball so hard it starts shedding sand, except in space. There's no one to hear it happen. What's truly mind-bending is how these trails influence the solar system's ecology. Every speck of dust an asteroid sheds joins an invisible river of cosmic debris, swirling around the sun in vast interplanetary dust clouds. Some of this material eventually rains down on Earth as micrometeorites, delivering trace elements that have subtly shaped our planet's chemistry over billions of years. Other particles get trapped in orbital resonances, forming faint rings around the sun that only specialized telescopes can detect. Asteroids, it turns out, aren't just passive rocks. They are active participants in the solar system's dust cycle, quietly seeding the void with raw material. But the biggest question remains: how many of these dust-spewing asteroids are out there? Recent surveys suggest they're far more common than anyone guessed. The Linear Project, which scans for near-Earth objects, has identified dozens of asteroids with faint but detectable dust trails. Some, like 311P/Pan-STARRS, even sprout multiple tails as if they're caught in a cosmic windstorm. The more we look, the clearer it becomes. This isn't an anomaly. It's a hidden norm, a secret life of asteroids we've only just begun to decode. The implications are cosmic. If asteroids contribute significantly to interplanetary dust, they might be the missing link in explaining certain meteor showers or the presence of rare minerals in Earth's atmosphere. Even more tantalizing, these dust trails could serve as breadcrumbs for future missions, guiding spacecraft to asteroids rich in resources or scientific value. Yet the most poetic revelation is how these trails blur the line between comet and asteroid. For centuries, we've classified these objects as separate species, one icy, the other rocky. But nature, as always, refuses to fit into our boxes. Active asteroids are the universe's way of reminding us that categories are human inventions, not cosmic laws. Every dusty trail we find is a whisper from the solar system's hidden machinery. a sign that even the quietest rocks are part of something far more dynamic than we ever imagined. Deep in the asteroid belt and beyond, cosmic alchemy cooks up minerals so strange they shouldn't exist, substances forged under pressures and temperatures that turn earthly geology on its head. At the top of this list is allobogdanite, a phosphide mineral so rare it's been found in just a handful of meteorites on Earth. This iron-nickel-phosphorus compound doesn't form under normal planetary conditions. It requires pressures exceeding 60,000 times Earth's atmosphere and temperatures hot enough to liquefy steel. That means every speck of allobogdanite we've discovered is a relic of asteroid collisions so violent they momentarily recreated the hellish conditions of a nascent solar system. But allobogdanite is just the beginning. Asteroids have delivered a catalogue of exotic minerals that read like something from a sci-fi novel. Take bridgmanite, a silicate so dense it makes up 38% of Earth's volume, but only exists deep within our planet's mantle. On asteroids, however, shockwaves from hypervelocity impacts can create microscopic pockets of this mineral right on the surface, essentially exposing planetary guts we'd otherwise never see. Then there's pangwite, a titanium oxide first identified in the Alend meteorite, whose crystal structure is so unique it's named after Pangu, the giant from Chinese mythology who hatched the universe from a cosmic egg. These minerals aren't just curiosities, they're puzzle pieces from the solar system's most violent moments, preserved in asteroid time capsules. What makes these substances truly baffling isn't just their rarity, it's what they reveal about asteroid interiors. Minerals like troilite, an iron-sulfur compound, suggest some asteroids once had molten cores that separated into metallic and silicate layers like miniature planets. Others, like schrebersite, are phosphorus-rich and may have played a key role in seeding life's building blocks. When exposed to water, schrebersite reacts to form phosphites, critical ingredients for RNA and cell membranes. Suddenly, these exotic minerals aren't just geological oddities, they're potential midwives to biology itself. The most mind-bending examples come from so-called ultra-high-pressure minerals like diamond-coated lonstellate. Found in the wreckage of asteroid collisions, this hexagonal diamond is up to 58% harder than its earthly counterpart, with a structure that could only form during planetary-scale impacts. Some specimens from the Popogai crater in Siberia contain both diamond and lonstellate swirling together like a cosmic marble cake, evidence of pressures so extreme they forced carbon atoms into entirely new architectures. Yet for all we've uncovered, the real treasure might still be lurking. Asteroid 16 Psyche, a metal world the size of Massachusetts, could harbor minerals we've never seen, substances forged in the cores of protoplanets long since destroyed. Missions like Psyche aim to hunt for these hidden gems, probing whether asteroids hold the keys to materials that could revolutionize everything from industrial drills to quantum computing. Every speck of these cosmic rarities whispers the same truth. The universe's chemistry lab operates on scales we're only beginning to fathom. The asteroid belt between Mars and Jupiter should be overflowing with cosmic debris, millions of rocks left over from the solar system's violent birth. But here's the problem. When astronomers calculate how much material should be there based on planetary formation models, the numbers don't add up. Over 99% of the belt's expected mass is missing, vanished without a trace. This isn't just a rounding error. It's a cosmic whodunit, one that's forced scientists to reconsider everything from planetary migrations to invisible demolition processes tearing asteroids apart from within. Some of the most compelling clues come from the belt's own architecture. The asteroids we do see aren't randomly scattered, they're clustered into families, groups with similar orbits and compositions that hint at shared origins. These families are the fragmented remains of ancient parent bodies, shattered by collisions over billions of years. But here's the catch. Even if you tally up all these fragments, they account for only a tiny fraction of the belt's predicted mass. That means most of the material didn't just break apart, it disappeared, either ejected from the solar system or ground into dust too fine to detect. One radical theory points to Jupiter's gravitational tyranny. During the solar system's chaotic youth, the giant planet's gravity could have acted like a cosmic slingshot, hurling asteroids into the sun or flinging them into interstellar space. Computer simulations show Jupiter's migration, a slow drift inward toward the sun before reversing course, would have destabilized countless orbits, clearing the belt with the efficiency of a celestial vacuum cleaner. This might explain why the belt isn't just sparse but patchy, with certain regions almost empty while others remain densely packed. Then there's the possibility of self-destruction. Asteroids, especially rubble piles, are fragile. Heat from the sun or collisions can trigger the warp effect, speeding up their rotation until they literally spin themselves apart. Over billions of years, this process could have turned entire generations of asteroids into drifting clouds of gravel, too small to reflect much light but still lingering invisibly in the void. Missions like Hayabusa 2 have seen this in action, capturing images of asteroids like Ryugu shedding material like a dog shaking off water after a swim. But the most haunting explanation involves a process called collisional grinding. Imagine two asteroids smashing together not with cataclysmic force, but in slow, repeated encounters, each impact chipping away at their surfaces like sandpaper on wood. Over eons, this relentless sandblasting could reduce mountains of rock to fine powder, scattering it so thinly that it blends into the background of space. Some estimates suggest that if this process runs unchecked, the entire asteroid belt could fade into near nothingness within another few billion years. The missing mass mystery isn't just academic, it reshapes how we view the solar system's evolution. If the belt was once hundreds of times more massive, its gravitational influence on early Earth could have been profound, possibly altering our planet's orbit or even delivering the water that fills our oceans. Every crater on the Moon, every mineral sampled from an asteroid, every computer model of planetary migration is a piece of this puzzle. And as missions like Lucy probe the Trojan asteroids and telescopes peer deeper into the belt's shadows, we're slowly unraveling the truth. The solar system didn't just form in chaos, it's still cleaning up the mess. Yet the biggest question remains unanswered. If the belt is vanishing, where's all the dust? Infrared surveys should detect the thermal glow of countless microscopic particles, but the numbers still fall short. That means the missing mass might not just be hiding. It could be gone entirely, a ghostly reminder of how little we truly understand about the forces sculpting our cosmic neighborhood. The asteroid belt isn't just a collection of rocks, it's a crime scene, and we're only just beginning to piece together what happened. Imagine an asteroid floating peacefully in space until the sun rises over its horizon. In an instant, the temperature rockets from -200 degrees to over 200 degrees Fahrenheit, a swing so violent it makes Earth's seasons seem tame. This isn't just a weather change, it's a slow-motion demolition, a process called thermal cracking that's quietly tearing asteroids apart one sunrise at a time. The evidence is everywhere, from the spiderweb fractures on Bennu's boulders to the scree slopes of loose rubble on Ryugu that look like avalanches frozen mid-fall. These aren't impact scars or collision damage, they're the unmistakable signatures of an asteroid being baked and frozen into submission. The physics behind thermal cracking is brutally simple. Most rocks expand when heated and contract when cooled, but in space, these changes happen almost instantly. On an airless asteroid, there's no atmosphere to buffer the temperature shifts, just raw sunlight followed by the black chill of shadow. Over thousands of cycles, this relentless expansion and contraction builds up stress in the rock until one day, a microscopic crack forms, then another. And another, like a sidewalk splitting under repeated frosts, the asteroid's surface gradually shatters into fragments, some no larger than grains of sand. Osiris-Rex saw this firsthand at Bennu, where boulders showed fresh fractures aligned like compass needles pointing toward the sun's most intense angles, a clear indictment of thermal abuse. But the real surprise, thermal cracking doesn't just create surface damage, it can reshape entire asteroids. On smaller bodies like Oumuamua, where gravity is barely a suggestion, cracked fragments don't stay put. They migrate toward the equator, piling up like cosmic beach sand until the asteroid bulges at its waist like an overinflated tire. Some researchers think this process could explain why so many asteroids end up with bizarre, spinning top shapes, their middles distended while their poles erode away. It's a feedback loop of destruction. Cracking creates loose material which migrates, which changes the asteroid's shape, which alters how sunlight strikes it, triggering even more cracking. The implications get wilder when you consider what's hiding beneath the surface. Thermal cracking doesn't stop at the exterior. It penetrates deep, opening pathways for solar radiation to reach volatile compounds like water, ice, or organics. On asteroids like Ceres, this might explain those mysterious bright spots, subsurface ices exposed by cracking, sublimating into space and leaving behind salt deposits like cosmic sweat stains. Meanwhile, carbon-rich asteroids could be cooking their own organic materials under this sunlight-driven pressure cooker, fracturing just enough to let radiation synthesize complex molecules in the cracks. And then there's the ultimate fate. Given enough time, thermal cracking doesn't just weather an asteroid, it dismantles it entirely. Models suggest small asteroids, especially rubble piles, could disintegrate completely within 1 billion years, their constituent boulders breaking down until they're nothing but drifting gravel. Even larger bodies aren't immune. Vesta's pockmarked surface shows signs of thermal stress fracturing that likely contributed to the avalanches seen in its craters. It's a humbling thought. The same sunlight that gives life on Earth could be the force that slowly grinds asteroids into cosmic dust. Yet for all its destructive power, thermal cracking might also be a creative force. Those fractures and loose grains, they're perfect traps for interstellar dust and organic molecules, which accumulate in the cracks like treasure in a vault. Some scientists speculate that these sun-baked fissures could act as primitive chemistry labs, where trapped molecules are shielded just enough to react and evolve. It's another reminder that in space, even the most violent processes can set the stage for something new, one crack at a time. So the next time you see a close-up of an asteroid's fractured surface, remember, those lines aren't just random scars. They're pages from a diary chronicling a lifetime spent cycling between fire and ice, each entry written in the slow, inevitable language of physics. And if we're lucky, decoding that diary might just reveal how the solar system's smallest bodies endure and ultimately succumb to the universe's harshest rhythms. For decades, astronomers have relied on spectral signatures, the unique fingerprints of light reflected by minerals, to identify asteroids without ever touching them. But some space rocks refuse to fit into neat categories, displaying spectral patterns that don't match anything in our meteorite collections. These spectral mismatches aren't just minor discrepancies, they're glaring anomalies, like finding a human fingerprint with an extra loop that defies all known records. The implications are staggering. Either we're missing entire classes of meteorites on Earth, or asteroids exist out there made of materials we've never encountered before. Take the case of asteroid 2006 9HY51. When scientists analyzed its spectrum, expecting the typical patterns of stony or metallic asteroids, they got something utterly unrecognizable, a jumble of absorption lines that didn't align with any known mineral group. At first, researchers assumed it was a fluke, an observational error. But then came asteroid 514-100 Pholus, a distant object with a deep red hue unlike any meteorite ever found. These outliers aren't rare exceptions, they're part of a growing list of spectral orphans, asteroids that laugh in the face of our classification systems. So where do these misfits come from? One theory points to the outer solar system's dark, icy frontiers. Objects like Pholus orbit far beyond Jupiter, in regions where temperatures are low enough to preserve exotic ices and organic sludge that never survived the trip to Earth as meteorites. When sunlight bakes these distant asteroids, their surfaces might undergo complex chemistry, creating tar like tholins or other compounds too fragile to endure atmospheric entry. That would explain why we've never seen their spectral twins in our labs. They simply vaporized or transformed on their way down. Then there's the possibility of extreme space weathering. Asteroids battered by eons of solar wind and cosmic rays can develop optical patinas, thin coatings of nanophase iron or other altered minerals that mask their true compositions. It's like trying to identify a painting while only seeing the varnish layer. The original colors are still there, but hopelessly obscured. Some spectral mismatches might simply be asteroids in heavy disguise, their true nature hidden under these cosmic makeovers. But the most tantalizing explanation, we're seeing fragments of vanished worlds. The early solar system was littered with protoplanets that fractured long ago, some with compositions unlike anything left today. If an asteroid is a shard of one of these lost bodies, its spectral signature could be a fossilized snapshot of a planet that never was. Japan's Hayabusa 2 mission found hints of this at Ryugu, where the asteroid's dark, carbon-rich surface didn't perfectly match any known meteorite group, suggesting it might be a relic of a parent body that no longer exists. The hunt for answers is complicated by our own planet's biases. Earth's atmosphere acts like a filter, ensuring only the toughest meteorites, usually metals or dense stones, make it to the ground intact. Delicate carbonaceous or icy material often burns up or fractures, meaning our meteorite collections are skewed toward a narrow slice of what's actually out there. It's like trying to reconstruct a forest ecosystem by only studying the rocks. You'll miss the flowers, the insects, the entire living tapestry. That's why missions like NASA's upcoming NEO Surveyor are so critical. By capturing high-resolution spectra of thousands of asteroids, we might finally spot patterns among these mismatches, grouping them into new families that reveal hidden chapters of solar system history. Every oddball asteroid we find isn't just a curiosity, it's a clue, a piece of cosmic driftwood washed ashore from uncharted territories. And as we keep searching, one thing becomes clear. The universe's recipe book for building asteroids has pages we haven't even glimpsed yet. The most explosive debate in modern astronomy isn't about black holes or dark matter. It's about a single, peculiar object streaking through our solar system and the audacious claim that it might not be natural at all. When Oumuamua, the first known interstellar visitor, was detected in 2017, its bizarre traits ignited a firestorm. No tail like a comet, yet it accelerated as if pushed by unseen forces. A shape like a cosmic pancake, tumbling end over end, and perhaps most puzzling, a trajectory that didn't quite fit the expected path of a simple space rock. Harvard astrophysicist Avi Loeb didn't just raise eyebrows when he suggested Oumuamua could be alien technology. He detonated a bomb in the scientific community. Loeb's hypothesis hinges on three anomalies. First, the acceleration. Comets speed up when ices on their surface vaporize, creating visible tails. Oumuamua had no tail, yet it gained speed. Loeb proposed it might be a light sail, a thin, artificial structure propelled by sunlight, like a boat catching wind. Second, its shape. Natural asteroids tend to be lumpy or spherical, but Oumuamua's extreme length-to-width ratio resembled theoretical designs for interstellar probes. Finally, its brightness. The object varied dramatically in reflectivity as it spun, as if its surface were flat and metallic, unlike the rough, irregular surfaces of most asteroids. The backlash was immediate and fierce. Mainstream scientists countered that Oumuamua's quirks could all stem from natural processes, its acceleration. Maybe hidden pockets of hydrogen ice which vaporize invisibly in sunlight. The odd shape, a fragment from a planet shattered by tidal forces, stretched like taffy during the cataclysm. The light variations, just a bizarrely elongated rock tumbling through space. Critics accused Loeb of sensationalism, arguing that extraordinary claims require extraordinary evidence, and Oumuamua's fleeting visit left too much uncertainty. But here's where the controversy deepens. Oumuamua isn't the only interstellar visitor behaving oddly. Comet Borisov, detected in 2019, looked like a typical comet until analysis revealed its water had unusual chemical ratios, hinting at formation in an alien star system with different conditions. If interstellar objects are this diverse, could some defy conventional explanation entirely? Even skeptics admit Oumuamua's properties sit at the edge of known physics. Its reflectivity was 10 times higher than typical asteroids, and no observed outgassing fully explains its acceleration. The debate isn't just about one object, it's about how science confronts the unknown. Loeb's detractors argue that invoking aliens shuts down inquiry, while his supporters counter that ruling it out prematurely is just as unscientific. Both sides agree on one thing: we need better tools. Future telescopes like the Vera Rubin Observatory could spot dozens more interstellar visitors, settling whether Oumuamua was a fluke or a hint of something stranger. Until then, this cosmic enigma remains the ultimate Rorschach test, a mirror reflecting our hopes, biases, and the thrilling possibility that we might not be the only architects in the universe. What makes this debate so pivotal isn't who's right or wrong, but what it reveals about discovery itself. Sometimes the most profound breakthroughs begin with someone daring to ask, what if we're not alone? And whether Oumuamua was a sail, a shard, or something beyond our imagination, it's already achieved one undeniable feat, pushing science to the edge of the unknown and forcing us to wonder what else might be out there, silently slipping past our telescopes, carrying secrets we're only beginning to dream of decoding. From organic molecules that rewrite the origins of life to metallic volcanoes erupting liquid iron, the 25 bizarre discoveries we've explored today aren't just curiosities, they're cosmic revelations. Each one peels back another layer of our solar system's strangeness, proving that asteroids are far more than simple rocks adrift in the void. They're time capsules preserving the chaos of planetary birth, chemical factories brewing life's ingredients, and even potential waste stations for humanity's future among the stars. Think about it: water ice hiding in the sunless shadows of rubble piles, diamond-like crystals forged in collisions violent enough to liquefy rock, and asteroids so fragile they could crumble at a touch. These findings shatter every textbook assumption about these nomadic worlds. They're not static relics, they're dynamic, evolving, and in some cases barely holding themselves together against the forces of space. Then there are the enigmas that still defy explanation: the color-shifting surfaces, the magnetic ghosts of long-dead cores, the interstellar visitors like Oumuamua that refuse to fit into any known category. These mysteries remind us that for every answer we uncover, the universe tosses us 10 new questions. So what does this mean for our understanding of the cosmos? If asteroids can be this wildly diverse, this unpredictably active, what other surprises are waiting in the darkness? Could there be asteroids out there with features we haven't even imagined, perhaps caverns filled with exotic ices, or surfaces coated in minerals that don't exist on Earth? And if life's building blocks are this common in space, how many other worlds might have been seeded just as ours was? The more we learn, the clearer it becomes. The solar system is weirder, more inventive, and more mysterious than we ever dared to guess. Asteroids aren't just bystanders in the story of the universe, they're active players, shaping planets, delivering life's ingredients, and occasionally throwing us a curveball that forces us to rethink everything. Now we turn it over to you. Which of these discoveries shocked you the most? Do you think we've only scratched the surface of what asteroids are hiding? Drop your wildest theories in the comments, because if history's taught us anything, the truth out there is always stranger than fiction.